Right, for our fourth example, we've got another set, same as the previous two, but we've got a new relation. And this time our relation is that x is a factor of y squared. So if we go through and we populate this relation, it's quite large, so it'll take me a while to write down all of the examples, but I'll skip through this bit as quick as I can. So our relation is then 2 to 4, 2 to 6, 2 to 8, 4 to 2, 4 to 8, 4 to 6, 3 to 6, 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6, 7 to 7, and 8 to 8. Right, here we go. Have I missed anything in there? No, I think I've got pretty much everything. Oh, no, I have missed one. So what you can see here is I've got 4 to 8, but actually we should have the reverses in here as well. Not for all of them, but for some of them. Because you imagine, so we have 2 to 4, we've also got 4 to 2, we've got 4 to 8, and we should also have 8 to 2, because 4 squared is 16, and 8 is a factor of 16. So we should also have 8 to 4 in there. 6 to 3, 3, 6 to 9, nope. Yeah, okay, I think that is everything now. Hopefully I haven't missed anything out. But what we're going to do slightly different to this one. First we're going to check for those properties that we did before, so we'll check whether it is reflexive, and yes, this is reflexive because it's got 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 8, 8. We'll ask, is it symmetric? And we've got 2 to 4 and 4 to 2, 2 to 6, and don't have a 6 to 2. But we don't have 6 then mapping onto anything else, so we don't have a counterexample. We've got 2 to 8. Do we have 8 mapping onto anything else? Nope. 4 to 8. 8 to 4. So yes, this is in fact a symmetric relation, because for x mapping to y, y maps back to x. Now we need to ask, is it transitive? So we've got 2 to 4 and 4 to 6. Do we also have 2 to 6? Yes, we do. We've got 4 to 2 and 2 to 4. Do we have 4 to 4? Yes, we do. 2 to 4, 4 to 8, 2 maps to 8. Yes, so this is a transitive relation. Because we've got yep, maps to y, and y maps to z, then x also maps to z. And finally, we have to check, is this anti-symmetric? So remember, our anti-symmetric example is that if 2 goes to 4 and 4 goes to 2, then 2 must be equal to 4. So if x goes to y and y goes to x, x must be equal to y. So this here, 2 to 4, 4 to 2, that is a counter-example, so this is not an anti-symmetric relation. Now we're going to go on with this, and we're actually going to use it to draw a directed graph, because what we've been doing is just looking at these as sets, but a lot of times you want to actually visualize this property. So if we wanted to do a directed graph of this particular relation, we'd start off, say, with the number 2 down here, and we would look for our first example. So our first example over here is going to be 4. And so to actually draw this, all we're doing is a directed graph going from 2 to 4. Just draw a little arrow down the middle of it like that. Okay. Next one is we have 2 to 6. So if we draw, say, 6 over here, we can have that mapping 2 to 6. You can probably see where this is going now. And we've also got 2 to 8 up here. 2 mapping all the way up to 8. That, and then we've got 4 to 2, so we just want to draw this line in reverse like that. We've got 4 to 8, so we want to draw that up like that. We got 4 to 6, draw a little line in there like that. 3 to 6, we don't have 3 yet, so let's draw 3 down here. And this is going to get a little bit messy, I do apologize. It's probably nicer ways of drawing this out. But if we go from 3 to 6, right, I'm going to draw it like that just to show that it's not connected. And 2 to 2. So if you're drawing a relation to itself, it's just a circle. 4 to 4, circle like that. 6 to 6, circle like that. 8 to 8, circle like that. 3 to 3, a little circle like this as well. Yep, something like this. And have we got everything? No. So we're missing our 5s and our 7s. So we just draw these as separate points out here. Little arrows going back to themselves. And I believe that is our directed graph done.